wanted to make a point about some other details, in particular the improper integral. So what this improper integral is going to be is an integral where either your function here is discontinuous between a and b, or one of your limits, if not both of your limits, are set to infinity or negative infinity. As an example, let's take the square root, or let's take 1 over the square root of the quantity x minus 1. Notice what happens when x is equal to 1. This is discontinuous, right? It's discontinuous at 1. Here, we've got the integral from -2 to 2 of 1 over the quantity x plus 1 squared. Well, at -1, this thing becomes 0. So we have a discontinuity at -1. And -1 is in that region, between -2 to 2. And in these first two examples, we have integrations taken up to infinity. So how do we handle these? Well, in this case, we're going to break it up into two integrals and use the limit. Excuse me. In this case, we're just going to set 1 equal to a and apply the limit as a approaches 1 from the right. Similarly up here, we're going to come up to this and say, hey, let's set b as our upper bound and apply the limit as b goes to infinity. Here, we're going to have -a to a and set a to infinity with the limit, right? So what does that mean? What does that look like? And what are these examples in particular? Well, in this case, you've got this weird hill looking of a function, right? And in this case, we just have an exponential decaying function. Question: what's the area underneath both of these functions? Do you think it'll be a number, or do you think it'll be infinite? So, go ahead.
I think infinite.
You think infinite? Makes sense, right? Because we're going to infinity, right? We're taking area under something that goes on to forever, right?
Yeah.
Exactly.
It makes sense.
It would make sense. That's what logic, what our personal experience would tell us, right?
Yeah.
So let's take this example I wanted to look at. Let's take this example here. The integral from negative infinity to 0 of 1 over the quantity 1 minus 2x raised to 3 over 2 power. We're integrating with respect to x. So we've got infinity here, right? And what we're looking at is this thing. We're integrating from here all the way to infinity, or to negative infinity, I should say. Folks at home, what do you think the area of this is going to be? What do you think this integral will come out to be? All right, well, since everyone at home is asleep, I'm going to go ahead and jump to this. First, start off with, how do we even solve this problem? We start by swapping out our negative infinity with an a and setting a limit as a goes to a negative infinity. Great, but what does that mean for our integration? Well, for our integration, that means you're going to go ahead and do the integral and carry those bounds over like you normally would. You're going to leave that limit alone for right now. Then you're going to apply these bounds. So at 0, 1 over the square root of 1 minus 2x. This thing is going to disappear, so you're going to be left with 1 over the square root of 1, which is just 1. And at a, you're going to get this thing, right? But we're taking the limit as a goes to negative infinity. And when we do that, this goes to 0. Because this gets really large underneath the radical, right? Square root of a really large number is going to be a really large number. 1 divided by a really large number that goes to infinity, that's just 0. So we get 1 minus 0. So the area underneath this curve is 1. The area between negative infinity up to 0 of this function is 1. It's counterintuitive, isn't it? This happens a lot in mathematics. In fact, something that we gloss over in this class is the fact that there are 2 different types of infinities. There's one that you can count to, and then there's the one that you can never, ever hope to count to. Chuck Norris knows very well how to count to the countable infinity. For anyone who's a millennial, it understands the Chuck Norris jokes. The uncountable infinities, those are really weird. So think of it this way. You have the infinity that you can count to in the sense of 1, 2, 3, 4, 5. If I do this forever, I would get to infinity at the heat death of the universe, right? Because I'm doing it forever. Infinity is forever in some sense, right? The uncountable infinity, on the other hand, is the idea that take the interval 0 to 1. Let's break it up. We're going to break it up to be 0 to 1/2 and 1/2 to 1. Now let's break those up. And let's break those up. And let's keep doing this. We can do this for as long as we want. But there is no way to break those up forever and expect that that will correspond to your counting numbers. So this is a whole long conversation in and of itself. But I just want to make this point. There were 2 different types of infinities to start off with. And what happens at infinity can oftentimes be counterintuitive, like the area underneath a curve as you go to infinity. That's really counterintuitive. So jumping back to all of this, the way we handle improper integrals, like I said, in the case where you go to an infinity in your bounds, you're going to replace that bound and apply a limit. Here we have the upper bound. Let's go ahead and replace it with b and then send b to infinity. Then we're going to integrate, keep those bounds on, solve as much as we can, then we're going to apply the limit. And similarly, these others two will work much the same way. In the case where we go from negative infinity to infinity, we break it up into 2 different integrals, and then we apply the first 2 cases. So we want to take the integral from 1 to infinity of 1 over x dx. First question, do we expect this to come out to be a nice number, or do we expect this integral to be infinity?
I don't think it'll be.
Well, this is going to go off to infinity. And in that way, we have an idea of convergence and divergence. If an integral comes out to be a nice number, then a number not like infinity, then we say that that integral converges. If it doesn't, if it goes off to infinity or negative infinity, then we say that integral diverges. So the idea of convergence and divergence is this comes out to be a good number, a number that we can write down, convergence. This comes out to be infinity or negative infinity, divergence. And in this case, we're going to say, cool, we've got the integral from 1 to infinity of 1 over x dx. Well, let's go ahead and replace this infinity. We're going to replace it with b. We're going to say, let's integrate from 1 to b the function 1 over x with respect to x. And then we're going to apply our limit as b goes to infinity. Okay, well, we know that just the integral of 1 over x, that's the ln of x. The ln of the absolute value of x. But we're integrating across positive numbers, so we can go ahead and just drop that absolute value, right? We don't have to worry about it here. But we do need to carry our bounds down. And that's what we're doing here. We're saying, okay, cool. I know that ln at 1, that's 0. And the ln at b, well, that's just the ln of b. So I have the ln of b minus 0. Well, I haven't applied my limit yet, but when I do that, the limit of the ln of b as b goes to infinity, well, that's just going to be infinity. So we would say that this integral diverges. Now, we've already seen this case, the one I just talked about that converges to 1. We replace our negative infinity with a, and we apply the limit as a goes to negative infinity. We solve this integral and keep our bounds, right? Then we apply our bounds. Then we apply our limit. And then we simplify. Hey, we got a nice number. This integral converges. And it converges so that it has an area of 1 square unit. That in and of itself is bizarre. So one way to think of this is if we were to draw this function accurately and to a decent scale, which I'm not going to be able to do, but I'm going to mock it up a little bit. Getting that all erased. One way to interpret this thing is, let's say each of my hash marks are perfect. And the distance between them is 1 inch. And they represent your traditional hash marks, right? Then if I could draw this function perfectly, and I can draw it forever, that area would be equal to the same area within a 1 inch by 1 inch square. That's one way to interpret it, which is insane when you think about it, right? If this was drawn perfectly to scale, so this is 1 inch, this is 1 inch, and we had each of these ticked off as it would be, right? X equal to -1, equal to -2, -3, so forth and so on. Y equal to 1, y equal to 2, so forth and so on. Then the area underneath that would be exactly equal to the area inside of a 1 by 1 square. Which again is insane when you think about it. I personally think this stuff is. All right, well, what about an integration like this? How are we going to handle this? First thing to notice is we could use substitution, right? right? So we're going to use u substitution here. Let's say u is equal to x squared. Let's go ahead and say negative x squared. Then du dx is equal to negative 2x. And du is equal to negative 2x dx. So putting all of this together, we get the integral of negative e to the u du. Agreed? Well, what do we do with our bounds? We start by noticing that we rewrote everything in terms of u, right? Here, everything's in terms of x. You have to go ahead and say, cool. In the limit, as x goes to infinity of negative x squared, this is going to give us what u goes to in that limit, right? What happens here? This goes to negative infinity, doesn't it? And when x is 0, u is also going to be 0, right? Agreed? Sorry, I'm almost done. So when x is equal to 0, u is equal to 0, and when x tends to infinity, u tends to negative infinity. So we rewrite this as the integral from 0 to negative infinity. Just get a little weird here, I know. But a point I should make out is they don't quite go about this the same way. I'm going to go about it this way. And I'm going to point out that because of this negative, we can flip this, couldn't we? We could go ahead and say, well, this integral, because of the rules of integration, is equal to 0, negative infinity to 0. E to the u du. Right? Well, what's that? I have to apply these new limit rules. Okay, let's substitute this all in now and say this is the limit as a goes to negative infinity of the integral from a to 0 of e to the u du. Okay. So I got something in my eye now. Cool. So this thing now, you know how to integrate this. This is just going to be the limit as a goes to negative infinity of e to the u plus a constant, but we're applying the bound, right? This is the definite interval, so we can go ahead and drop that constant. Say from a to 0. But this is going to give us the integral, or my mistake, the limit as a goes to infinity, negative infinity, of e to the 0 minus e to the a. This is just equal to 1 minus e to the a. So we have the limit as a goes to negative infinity of 1 minus e to the a. And what happens there? As a goes to negative infinity, this term is going to disappear, right? It's going to go to 0. This is equal to 1 minus 0, or 1. Checking out answers. It does in fact go to 1. Now, they've done something here. The way they went about this was, instead of having to worry about changing your bounds, they said, instead of changing these bounds, we're going to rewrite this as this integration from e to the u, and we're going to keep x equal to 0 and x equal to infinity. Then we're going to keep moving through that. Does that make sense what I mean? So they pull out everything, do the integration, do the substitution back, then they apply the bounds. Whereas what I've just done is went ahead, did the substitution, and changed the bounds so that we still got everything the same. Cool? And this is one technique to use when you're using a U substitution. You don't want to change your bounds back. Then you can change, or if you don't want to have to worry about your bounds and making sure everything gets changed back the right way, you can change your bounds and integrate and not have to worry about that. Is that cool with everyone? And sort of. This is a technique that usually only gets taught in like Calc and Calc 2. But this is a decent problem to kind of give you the juxtaposition of the two. Now, in the case where you have a discontinuity, maybe your discontinuity is at B, or maybe it's at A, maybe it's in between the two. I'm just going to apply a limit. In the case where your discontinuity is at B, your upper bound, then you would take the limit as sum C approaches B from the left. If the discontinuity is at your lower bound, you would again replace it with C and take the limit as C approaches A from the right. Or maybe your discontinuity is in between. Then you would break up your integral and apply these limits accordingly. So, notice here we have a discontinuity at our lower bound. So we're going to rewrite this now. We'll say this integral, this improper definite integral, from 1 to 2 of the quantity x minus 1 raised to the negative 1/3 power integrated with respect to x. This thing is going to get rewritten. Rewritten, since we have a discontinuity at our lower bound, as the limit as C approaches 1 from the right of the integral from C to 2 of everything we have originally. Blah, 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 blah. The quantity x minus 1 raised to the negative 1/3 power integrated with respect to x. Cool. Now, we can apply the integration techniques that we know. So, jumping forward, check it out. They do the exact same thing, don't they? Say, hey, replace 1 with C and apply a limit as C approaches 1 from the right. Then do your integration, apply your bounds, then apply your limit. And when we do that, notice what happens is here you go from y equal to infinity down to y equal to 1 in this case, right? Yeah. So we go from y equal to infinity down to y equal to 2. We have this giant area that actually only turns out to be 3/2 units squared. So if each unit was an inch, this would only have an area of 3/2 inches squared. That is insane. Now, we could have a slightly different problem where, in this case, where's the discontinuity at? Well, it's going to be at our upper bound, right? Because x squared minus 2x, well, minus 2x is like x squared only when x is equal to 2. So we're going to have to apply that limit technique by replacing 2 with c and taking the limit as c goes to 2 from the left. Then we integrate. We come down here and we apply our bounds like we normally would, and then we apply our limit. Right? So you apply the antiderivative, then you apply the bounds, and then you apply the limit. Now in this case, we're discontinuous at x equal to 0, but we're integrating from -1 to 2. So we're going to have to break up our integral into 2 different parts. The part from -1 to 0 and the part from 0 to 2. Then we're going to have to replace this part with the integral from -1 to c, applying the limit as 0 approaches, or I mean as c approaches 0 from the left. And then this part is going to be the limit as c approaches 0 from the right of the integral from c to 2. Now, one place where this has to be used is just talking about probabilities. The area underneath this curve has to be 1 when you take it from -infinity to infinity. This is the normal distribution curve. And because probability of an event happening that's normally distributed has to be 1, we know the integral of this thing has to be 1. So we get the integral from -infinity to infinity is equal to 1 of this function. Just some fun facts about how this stuff gets applied. Having said that, I think I am going to leave it there. This last little bit here, section extra. It's just stuff about partial fractions and logistic curves. That I thought might be useful or interesting for some people. Partial fractions usually show up in cases like this, where you have to break up this fraction into 2 different parts. And this explains how to go about it. It sometimes shows up with different types of integrations. So for example, here, we don't have an immediate way of breaking this thing up. Not that's nice anyhow. So the question becomes, okay, what do I do now? Like, how am I supposed to integrate this if I can't break it up otherwise? Well, you could use partial fraction decomposition, get something that's workable, and when you do that, then you can integrate. And this just walks through how to do that. Like I said, I don't believe I have any homework problems that actually require this, but I wanted to let you all have access to this information if you wanted to use it or find it. It's just good enough to know. But having said that, that is all I got for the lecture today. If y'all have questions, feel free to ask.